Okay, this is going to be a very quick review of Chapter 1 of this book. So first of all, we're going to talk about vectors as basically just ordered pairs like this, or ordered triples, or you can have 4. And we're going to use boldface to indicate a vector like this. Sometimes if you're writing it on a board, you'll use an arrow instead, but otherwise use bold like this. Sometimes you'll use an arrow like that. Scalars are just elements of R1, not basically they're not vectors. So we have the definition of when two vectors are equal, because she says in order to do anything interesting, first you have to know when two vectors are equal. So if A and B are equal, it means that A1 has to equal B1, and A2 has to equal B2, and so on. Then we can talk about addition. We can say that the sum of A and B, and we add them element by element. So here's A, there's B. This is the element by element addition. Then once we define addition like that, we can prove some properties. For example, we can prove that A plus B equals B plus A. We can prove this one, which is called associativity. We have a special vector denoted 0, and that has the special property that if you add it to any vector, you get A back again. Scalar multiplication is an operation we can define where we take a scalar, which means something in R, and we multiply it times A, and this is what we mean by multiplying a scalar times A. And they have an example here. K equals scalar is 7. Oops. Then we can also give a kind of a geometric interpretation of a vector. So that sometimes is useful, and also I think that may be where the notion of vector originally came from, was the geometric idea of a vector. So we can say that a vector is just a point in the plane. So if it's R2, it's here. If it's R3, it's there. And that's a valid interpretation, geometric interpretation. But we sometimes, she says that if you want to talk about vector addition, sometimes it's kind of more interesting to associate a vector with an arrow. So an arrow means you start at 0 and you go to here, and that's the vector. So we can say that the vector A1, A2 is also this arrow. And if you take that point of view, you can also say that you can get basically the same point here if you tell what the angle is, so the angle from here to here, and the distance you have to go out, or the length you have to go out. That will also bring you, if you specify that, you can also specify so that you come to this point. So we could identify a vector equally as well with the angle that it makes with the x-axis, the positive x-axis, and the length of the vector. Now that doesn't actually make any sense if you're talking about that special vector we called the 0 vector. So that doesn't have any angle, but except for that one, that this interpretation makes sense. Now a little bit of confusion, but in physics they don't say that the vector has to begin at the origin. So there is this vector like this, but these are all considered the same vector. So all that means is in physics you get all these extra copies, so to speak, of this vector. So if we had just our original interpretation going from 0 to there, these wouldn't be there, so they don't really conflict with our interpretation, but physics allows them to be translated. So they have to keep the same length, and they have to keep the same angle, but they can be, so to speak, translated. And they use the parallel translate. So if you do that, then you can say, okay, what do I mean by vector addition? Now you're allowed to move these vectors around. So you can take your take one of your vectors. Like if you want to do a plus b, so you have an a and a b, you can take one of them and then take the other one and put it at the tip, put its base at the tip there. So you do this, and then it turns out that a plus b will turn out to be that. Now you actually have to prove that, but it will turn out that this is their sum. So that's kind of a nice picture of what the sum means. And there's another way to get the same thing. If this is a and this is b, you can also do this so-called parallelogram. So you form this parallelogram. You can see that it's really the same thing as taking the b over here and putting it over here. But anyway, you can also visualize it this way. We also have a visualization using this same kind of these kind of floating vectors. We can also visualize scalar multiplication. So here's a vector a, and if you multiply it by a scalar, for example, the number 2 is a scalar, what does it do? It just moves it, it just stretches it in the same direction. It doubles the length. So it doesn't affect the angle, but it changes the length. And this would be multiplying the same a by -3/2, so that will bring it this direction. I guess I don't know if you want to say that changes the direction or not. Okay, we also have something which we define called the displacement vector. And given 2 points in R3, these are not really vectors, they're just points. But given any 2 points, we can define the displacement vector, which is denoted like this. But what is it? So here's the point P1, and here's the point P2. We could call them vectors, or we just call them points. And the displacement vector is the vector which goes from P1 to P2. And to get you can show that this vector will, if P1 has these coordinates and P2 has these coordinates, then the displacement vector will be x2 minus x1. So this minus that, and then this minus that, and z2 minus z1. Here she says that because vectors have a direction and a magnitude, they're useful in physics for things like velocity, where we say velocity is speed in a particular direction, or acceleration, and force. Force has a magnitude, a size, and it also has a direction. So you can use vectors to represent force. So here's an example of physics situation. So suppose you have a particle here, and it has a velocity according to this vector here. So this tells you, the length of it tells you the speed of it, and the direction tells you the direction. So you can ask, where will the particle be? And if the speed is given in, what do they give the speed in? Whatever. The speed is in second, t is in seconds, so speed is in meters per second. So in 1 second from here, it will have gone to here, because the tv is 1v, and then 2 seconds it'll be twice that. So the position will be given by that. So looking at some of the exercises, they're easy. Sketch the following vector, so just sketch that and this. Sketch this. Well, that's a little hard because it's 3D, but section 1.2 is about the standard basis. So this is a vector, and this is also a vector. And these two vectors have special symbols, I and j. So this goes along the x-axis, and this goes along the y-axis. And because we talked about linear algebra, you'll know that these two vectors span R2, and that means that any other vector A can be written as a linear combination of these two. So here. So anyway, if this is the vector A, we can just, then A can be broken down into these two, which then can be written like this and like this. So we wrote them in terms of I and j, So here's I and j, and here's A is written as the sum of a multiple of I plus a multiple of j. And here we have I, j, and k. The same kind of thing there. Okay, the next thing is parametric equations of lines. So we can give an equation of a line like this, y equals 3, or more generally, like that, or it can be rewritten like that. If you said y equals 3 and you were talking about 3 dimensions, then that's not the equation of a line. That's the equation of a plane, but we'll see that later. So we want to talk about what are called parametric equations of lines. Slightly different way to write the equation of a line. Or maybe I shouldn't say slightly, it's a different way. Okay, now here is an equation given, here we have a function of t called f. We have another function of t called g. So, and here we have the xy plane, so t doesn't appear in this picture. So, but if x is, and this is normally the t means time. So this, I guess this kind of thinking came up when they were thinking of time. So in other words, we're saying x is a function of time. The x coordinate is a function of time, and the y coordinate is a function of time. So in that case, if you know what t is, then if you know what this function is, you'll know what x is, so, and you'll also know what y is, so you'll know where at each t, you'll know where the dot is, or where this is usually we're talking about some object or some particle. So we'll say we know where the particle is. So these two equations together will tell you where the particle is at a given t for a given time. So these are called parametric equations so at different t's it's going to be at different places, so it's going to move around. So it might move around in a circle or whatever, it's just going to move. It's going to have a particle moving around. So, but these two equations together are called the parametric equations for the curve. So these two are the example here. So here we have x equals 2 cosine of t and y equals 2 sine of t. And we're going to restrict t to be between 0 and 2 pi. And if you know about cosine and sine, when t equals 0, let's just do when t equals 0, so cosine of 0 is 1, and the sine of 0 is 0. So this is going to be 2 times 1, which is 2, and this is going to be 0. So it's going to be 2 comma 0. So that's where when t equals 0, it's going to be at 2 comma 0. So this, I guess, is 2 comma 0. And then you can let t equal other things. And what's going to happen is it's going to take on different values moving along this curve up to here and then around. And it'll come right back to here at 2 pi. Actually, this is less than or equal to, so we don't get we don't get the overlap. I guess they want to avoid the overlap. So it can't equal 2 pi. So now we can use the same kind of thing when we have 3 dimensions. We can say if we know x is a function of t, y is a function of t, and z is another function of t, then if we know t, we'll know the x, y, and z coordinates. So we can say we know the path. So this will describe some curve in 3 space. So we weren't really able to do that before. We saw that y equals 3 allowed us to define a line here, but we didn't really know how to define, or even y equals mx plus b gives some kind of line here, or some kind of curve here maybe, if it's some other way, some other equation, but we don't really know how to get a line, so right now, in the 3 dimensions, but now we do. With this method, we do. So they say that the advantage of using parametric equations, there's 2 of them. One is that you have the sort of the same way, whether you're in 2 dimensions or 3 dimensions or 10 dimensions, you sort of have the same way of describing a path or a curve in that space. And also they give you a direction, right? As t increases, the point is moving along. So when we just have a circle, forget about this method of defining a circle. If we just have a regular circle, there's no direction for the circle. But if you want to have a direction, this will enable you to have that direction. You can ignore the direction, so this gives you something extra that you can use, but you don't have to use. But it does give you a direction. And they say this even works in R128. So how can we use this parametric equations method to describe a line? How do we get exactly a line? I mean, we got different things. We got a circle and so on, but how do we specifically get a line using this perspective or this method? So like a line in R3, so they say if you have a line in R3, you can specify that line if you have two pieces of information. So if you know a point on the line, and you also know a vector A which is parallel to the line. So it doesn't actually, the vector A could be here, but as long as the line is parallel to A, there's only one line that will do that. If it goes through this point and it's parallel to A, then we've specified a specific unique line. So here's the same picture again. We have P0 and we have A, but now we've drawn in some other stuff as well. And basically we want to get an equation for our line. We don't have the equation yet, but we basically want to write an equation for any P that is on the line. So what can we say about this P? This P is, I want this P to lie on the line. So what can I say? I can say that I can get to P. So if I start here, I can get to P by just moving some multiple of A, and that will give me the P. So any P that's on the line will have that property. And any P that's not on the line, like a P over here, you can't get to it by doing that. You can't start here and move in the direction of A and get to here. So we can say that any P that's on the line, we're going to write a condition saying that any P that's on the line is equal to P0 plus, now we're going to be thinking of P0 as a vector. So P0 plus, well, you don't have to think of it as a vector yet. Anyway, P0 plus TA for some T. And that will get you, and that's a way to say that whatever satisfies that will be a point on the line. So now think of P0 as a vector, and let's call it, let's say it's OP, it starts here and goes to here, and we'll call it B. So now let's just write down what we just said. So we're saying we want to get this point P, but we're going to, okay, one more thing, we're going to call P actually the vector OP, and so we'll call it R. So R, we want an expression for R. So R, which is OP, is equal to OP0, or B, plus TA. So this gives us, and this would be called a parametric equation, a vector parametric equation for this line. It's called parametric because we have this T there, this T parameter, and of course it's vectors because it's all done in terms of vectors. And also, as I said, we can call this B and make it even sort of more obviously a vector. So we can call B, OP0, we can call that B. So we get this. And we put in R of T just to remind ourselves that R, this depends on T. It's B plus TA, B plus TA. So just to give this a little bit more specificity, so P is the point here, but we'll call it P of P is, has the coordinates X, Y, Z. That's a little bit strange, actually. P of X, Y, Z, I guess, but I want to say that P equals X, Y, Z, actually. But anyway, I won't worry about that, but I think that's what she means. And P0, they're giving it specifically, calling it, I guess they're doing that the same thing here. So maybe that's just the way they're writing it. So the coordinates of P0 are B1, B2, B3. It doesn't mean P of or P0 of. I guess this just means these are the coordinates of P0. These are the coordinates of P. And so if B, if this is B, then and these are the coordinates of P0, then B equals B1I plus B2J plus B3K, right? That's how you get to here. And it's parallel. So A has these coordinates, A1, A2, A3, or those components or coefficients. Okay, so let's not get confused with all that. Let's just go back and say that what we said is R, or this point P, is equal to, starting at P0 and going some multiple of A. So R is equal to starting at P0, which just means B, plus TA. However, now we're going to use all those subscripts and coefficients and so on. So it was R B1 plus TA, but these were the what do I call them? The coefficients, or the components of B, and these were the components of A. So we get this, and then we collect the I with the I, and here's the I with its two parts together. Here's the J with its two parts, and so on. And remember, we said that P, or OP, had just the X without any subscript, the Y without any subscript, and that's this part here. So what we're saying is this, which is here, is equal to this. And then we can just say, well, the I coefficient on the left has to equal to the I coefficient on the right, and the J coefficient on the left, which is Y, has to equal the J coefficient on the right. So we get these three equations. So finally, we get the parametric equations sort of in the standard form, not in the vector form, for our line. So it looks like this. So what we see is that the x-coordinate is basically linear in t, right? It's like mx plus b, that's linear. This is the same thing, a1t plus b1. And y is also linear in t, and z is also linear in t. So those give us a line where t is any real number. So this is, so for a line, that's a line in 3 dimensions, which we didn't actually accomplish before. And you can see sort of the extension for a line in any number of dimensions, which is here in Rn. So we don't call it x, y, and z anymore. We call it x1, x2, xn, and so on. So like we said, we can do this kind of thing for any number of dimensions. And also we get, the other benefit is that we get a direction for our line. So as t increases, the point is moving in a particular direction on the line. So here's an example. So to find a parametric equations of a line through a point, so we need a point, and parallel to a vector, so we need a vector. So it was R B plus T A, wasn't it A? Yeah, R is B plus TA, B plus TA, so they called it A. So we write R is B, here's B somewhere, B plus T times this, so that's that. And then they collect the I's, the J's, and the K's here. So they get this, and then they just say X equals, well, over here, this is X, sorry, it's XI plus YJ plus ZK. So we equate the I parts, the J parts, and the K parts, and we get this. So this is the parametric equation of this line, or the line that's specified in this example. Okay, example 4 is basically the same thing, but here they say find the parametric equations of the line through these 2 points. So before, in the last example, they gave us not 2 points, but they gave us 1 point and parallel to A, right? Now they're giving us 2 points, so we have to figure out what A is by ourselves, but that's not too hard. We just figure out the displacement vector between these 2 points, and that's RA, and then you can do the same thing that we did here. So you can look at that yourself. So they do it. And then after they do it, they say that you can see after doing that example that if you have 2 arbitrary points, that the parametric equations will turn out to be this. So I don't know, what is this? A1 comes from here, I guess, and this is B1 minus A1 times T. I guess it could be, obviously, this could be B1, and these could be reversed. But anyway, so you get an equation like this, apparently. And of course, it could also be written like this. You take P1 as the first, as the given point, and then you, for your vector that you want it to be parallel to, you just take the displacement vector, and so you get this. Or if you want, it could be the displacement vector could be in the opposite direction. You start with P1 and P0. Here it was P0, P1. Either way is okay. But the fact that either one is okay, or going back to here, actually it turned out that there were 2 solutions, because we could choose the initial point to be P0, we could choose the initial point to be P1, or there are actually many different solutions. So that tells us that the parametric equations for a line are not unique. You could get one, you could get another one, there are other ones that you could get as well. So they said that's kind of a problem in the sense that we don't know how to check our work. But they say in general it's not so easy to do, but in the case when you're talking specifically about parametric equations of lines, there are 2 approaches that you can. So if you have 2 sets of parametric equations, how can you show that they're both, if you think that they're both the same line, how can you show that? So one way is to produce 2 points that lie on one of them, and then show that those same 2 points lie on the other one. That will assure you that you're describing the same line. And there's one other way, and that is to use what's called the symmetric form of a line. Now, this so-called symmetric form will be unique. So, going back to the original description of our parametric equations here, which was just for a general situation, not specifically any particular numbers, we can solve each of these for t. You can solve this for t, you can solve the second one for t, and the third one. And then what you get, then you can equate all 3 of what you got because they're all equal to t. So they solve those 3 for t like this, and then they can equate these 3 because they're all equal to t, and this is called the symmetric form. So if we look at the example that we just looked at before, example 4, so taking here, we can solve for t, and we can equate what we get. We'll get something, and if we do it here, we'll still get the same thing. So I guess the first time we get this, the second time we get this, but these are basically the same. They said you can add 1 to each side of the second form. Anyway, we can figure out that these are the same. And so they say, in general, symmetric forms for lines can differ only by a constant term or constant scalar multiples, or both. So the symmetric form will be unique. I guess that has to be proved, but I'm not sure she does that here. Then she mentions that the symmetric form is actually 2 sets of equations. So we have this equals this, and then we also have this equals that. So that's 2 equations, which she writes like this and like this. And she says this kind of illustrates the fact that, as we kind of expect, that when we're in R3, in order to get the equation of a line, you're going to need two equations. Like one equation gives you a plane, and another equation gives you a plane, and then the intersection of those two planes will be the line. And she says this kind of illustrates that you need two scalar equations. These are scalars, there are no vectors in here. Whereas we only need a single vector parametric equation to get a line. We already saw that in this picture here, or this equation here. This is a single vector parametric equation, but if you don't want to use vectors, you're going to need two scalar equations to identify a line in R3. Okay, so we have two examples of using these parametric equations for lines. So they say find out where this is a set of parametric equations for a line, and this is a plane, and we want to find out where this line intersects this plane. So the reasoning is that we need to find a t such that the x, y, and z that we get from using that t will be in the plane, in this plane. So we want to know which t that will do that, if there's any t that will do that. So we just substitute x for t plus 5, y for this, and z with this. So we get this. And now we solve this for t, and apparently t equals -2. So it means there is a solution. And so setting t equal to -2 in the parametric equations will give us a point. I guess it gives us this point, and we can check to see whether that actually lies in the plane, and apparently it does. Okay, the next example using parametric equations is to find, this is going to be a line and this is going to be a line, find where they intersect. So we need to find something here, an x, y, and z over here, and we need to somehow get the same x, y, and z over here. Now one thing is a little confusing, and that is this t has nothing to do with this t. So we're going to rename these as t1 and t2 because they're not related. This is just t for this line, and this is t for this line. They have nothing to do with each other. So don't call them both t. So what we want is a t1, which will give us a certain x, y, and z here, and a t2, which will give us the same x, y, and z here. So what we want is a t1 such that t1 plus 1 equals 3t2 minus 3, because that means that the x's will be the same for that t1 and t2. But we also want these to be, this side to equal this side, and this one to equal this one. So we write that down like this, and now we have to solve for t1 and t2. So we have three equations and two variables, t1 and t2. Now there's no guarantee that these two lines do intersect, and just as there's no guarantee that there's a solution to this. Right? This could be over-specified, like too many restrictions, and there's no solution. But they do solve it. They do, they figure out here what t2 is in terms of t1, and then put that in here and keep solving. And it turns out that you get this, and you just finish the calculation, and it turns out that it is solvable, and this is the x, y, and z, which are common to both lines. So next is parametric equations in general, so not just for lines, but for other shapes. So like here's a shape, and it turns out that finding the parametric equation for this is not too hard, whereas doing it without using parametric equations might be quite hard. So you can read through this. This is like if you roll a ball, it rolls along and you have a fixed point here, you can ask where, what's the path of that fixed point? And it's a shape, but how do we get the equation of that? Turns out if you use parametric equations, which I'm not going to go through, you get these. And here's another example. If you unwind an adhesive tape from a non-rotating circular, anyway, so you can do that. You can ask what's the path and how can you describe it? So it's this kind of shape, I guess, but how do you describe it? And it turns out with parametric equations, you can do it fairly easily. Okay, for the exercises, they say write the given vector using the standard basis. So how do you write this is in this kind of notation? So obviously it's 2i plus 4j, and similarly with the other ones. And then how do you write this? Using this kind of notation, obviously it's 1, 1, negative 3, and so on. Next one is, suppose we have these two, a1 and a2, write b, which is equal to 3, 1, in terms of a1 and a2. So from linear algebra, we would say that we're writing b as a linear combination of a1 and a2, but anyway, just do it. Then here's do it for a different b. And then they say show that any vector, in other words, show that, they're asking you to basically show that a1 and a2 form a basis, because they're saying show that any vector b in R2 can be written as a linear combination of a1 and a2. Okay, in 13 through 18, they're giving you some practice with parametric equations. So they want you to find the set of parametric equations, or a set of parametric equations that describe whatever. So here is the line in R3 through this point and parallel to this. So do that. Here's a similar example, but it's in R2. And here's an example where they don't give you the vector that it's supposed to be parallel to. They just give you the point and another point. And here they ask you to get the symmetric form for the line that has these three as its parametric equations. And in 25, they give you the symmetric, and they ask you to go backwards and find a set of parametric equations. That shouldn't be too hard either. So you should try all of these. And you can check to see whether you can do some of the other ones as well. Okay, now we define something called the dot product, which is a kind of a multiplication for vectors. One type of, we're going to actually define at least two types of multiplication for vectors. So what do we mean when we combine two vectors in this way? Use the so-called dot product. The other one is going to be called the cross product or vector product. But that is only works for R3, but the dot product works for any Rn. Or it works for, I should say it's defined for anything vectors in Rn, but the cross product is only defined for vectors in R3. The cross product has to do with physics. It probably comes about from physics, and of course physics is usually working in R3, so it makes sense that, it seems likely that they're going to define something that is useful in R3. So here's a definition of the dot product. It's also called the inner product. It's also called the scalar product. And here's an example from R3. But this will work, this dot product is defined for any n, r, for any r, for any n, Rn. So anyway, suppose we have two vectors in R3. So here's a vector, which looks like this. Here's another vector, which looks like this. So what do we mean by this dot product, A dot B? What do we mean by that? We mean take A1 times B1, do that, and then also take A2 times B2, and then also take A3 times B3, and add these three up. So that's what we mean by the dot product of these two vectors. And in R2, it would be, you wouldn't have the extra, you wouldn't have this there, and you wouldn't have this there, so you wouldn't have this there, so you just have this part. That's when A and B are like that. So as a quick practice, suppose you're in R3, you have this vector and this vector. What do we mean by the dot product? Again, we just mean multiply 1 times 2 and so on, do that, and you get this number. Here's another example. Suppose you're expressing your vectors in terms of I, j, and k. You have 2 of them, and you multiply them. What do you get? You can do it, and you get 5. Okay, so now you see why it's called the scalar product as well as the dot product, because you get a scalar at the end. You get 5, you get 15. So it's important to note that is, when you take two vectors and you combine them using the dot or the dot product, you don't get a vector back, you get a scalar. So that's why it's sometimes called the scalar product. So here they say it produces a single real number, not a vector. So that's the dot product, but the cross product will be different. That will give you a vector. When you take two vectors and you do their cross product, you're going to get a vector. But the dot product gives you not a vector, just gives you a number or a scalar. Okay, but we haven't gotten to the cross product yet. So what kinds of properties can we get for this dot product? So one is that if you take a dot itself, it's never going to be negative. And you can see that because if you do a times itself, it's going to be a1 squared, because b1 is going to be a1, so it's going to be a1 squared, a2 squared, a3 squared, and when those are all non-negative, when you add them, you're still going to get non-negative. So a dot a can never be negative, and the only time a dot a can be 0 is if a is actually the 0 vector. They're doing this in R3 or R2, but actually it works for Rn. We didn't talk about the definition for the dot product in Rn, but I think you can see what it's going to be. If you had R4, this would be A1, B1, A2, B2, A3, B3, and A4, B4. So anyway, you can see how it's going to extend to R4 and Rn, and these properties will hold whether you're talking about R3, R2, or Rn. So we just did the first property. The second property says that you can reverse the order, and that's pretty obvious, because if I reverse the order, then I just get B1, A1 here, B2, A2 here. So that's pretty obvious. And here's another one. This is kind of like a distributive. So if you take A dot B plus C, you can break it up like this. And here's a scalar multiplication of A dot B, says you can take the k out, and you can move the k around, basically. And the proof, you should read these proofs to see how they're proved, or at least read this one. So it says, thus far we have introduced the dot product as purely an algebraic construction. So it turns out that its geometric information or interpretation is interesting. So first of all, suppose we have a vector A. This is not the dot product yet. Just suppose we have a vector A. We haven't really mentioned what we mean by the length, or how do we calculate the length. But by the Pythagorean theorem, like suppose we didn't have this here. Suppose it was just A1, A2, we just 2 dimensions. Then the length of A by the Pythagorean theorem that we all know is equal to this plus that square root. And for 3 dimensions, it turns out to be the same kind of thing. So this is the length according to the Pythagorean theorem, and we denote length of a vector this way, with these double bars around it. But if you look at this, you'll see this. But that should remind you of what we just sort of did up here when we were proving that the only way that I'm sorry, that this has to be positive. Why? Because we did this. We did A dot A. What did we get when we did A dot A? We got this, which is actually this. So what's inside here is what? Is A dot A. So that means that the length of a vector A, this part is A dot A, it's the square root of that. So the length of a vector A is the square root of A dot A. So that's what this says. That's what this says. So the length of a vector A is the square root of A dot A. By the way, they give you a little bit of reasoning for why we define length as we just did here, if you want to read that. So anyway, this equals that, or if we square both sides, we get that A dot A equals this squared. So we get this. So that's another interpretation of what we mean by A dot A. So A dot A is this new thing that we're talking about called the dot product, and now we have an interpretation of it as the length squared. Okay, now remember, length is not a vector, it's a number, and squaring it again is a number, and that conforms to the fact that we expect this to be a number. Okay, now turns out now with the dot product that we will be able to define the angle between two vectors in terms of the dot product. So of course we already understand what we mean by the angle between two vectors, so this is not so exciting, except that now we can use that definition for n-dimensional vectors, and we still have a definition or meaning for the angle between two vectors. And as in all good definitions, when you go from Rn to R2, you should get exactly the same meaning as the normal meaning for the angle between two vectors, even when you use this definition. So we want to show this relationship, and that's this theorem here, because if you just solve for the cosine of theta, you get the same thing we just saw. So this says if A and B are any two vectors, then A dot B equals the magnitude of A times the magnitude of B times the angle between them. So first they rule out the cases where either A or B is the zero vector. So if A is the zero vector, then A dot B will give you 0. And also the length of A is also 0, so you get 0 equals 0. So that's true in the case that A is the zero vector, and the same thing as if B is the zero vector. So now we can talk about the cases where neither A or B is the zero vector. So we let C equal B minus A. So in the picture, that means here's A, here's B, and this is C, which is B minus A. Now I always can't remember, does B minus A go from A to B, or does it go from B to A? And the way I check it is that which do I have to add, A or B to this to get B? So I can see that if I add A to this expression, I'll get B, because the minus A and the A cancel out and I'll get B. So that means if I take this plus A, I should get B, so that means it has to go this way. So the B minus A, that's how I remember it, or that's how I see it, is goes from A to B. So this is a triangle, and if you remember, we had something in geometry called the Law of Cosines, which tells the relationship of the lengths of A, B, and C. Now by lengths, we mean this. So this is the length of C, the length of A, the length of B, and this is the Law of Cosines. So now we do some stuff here. We write this as A dot A, remember, and this as B dot B, and this is C dot C. We get this. Now we do some, what else do we do? Now they say since C equals B minus A, C dot C equals that, And then this is some of those properties that we had about dot products, that you can kind of split them up and distribute them and so on. So you get this, or for C, or actually for C dot C. And they mentioned that that comes from properties 3 and 4 of dot products. So now we take this for C, and we put that in here. And that gives us now this. And then I guess do some subtracting and so on. You get this, and then you get this. Okay, so by various properties. So we get this equals that, and that gives us what we were looking for, which is this equals that. And that gives us this, which is tells us the angle. So this works when we're talking about R2. It also apparently works for R3, but for Rn, there is no such thing as the angle. So there's no law of cosines for that, but we just use this to define what we mean by the angle in Rn. And for R2 it works just fine, so it doesn't contradict our normal idea of angles. So that will make a mathematician happy. And they say this has the inverse cosine, and we have to worry about something about, I don't know, inverse cosine, is it a function or not? And it's only a function if you restrict theta to between here and here, but we're doing that anyway, basically, when we're talking about angles. So as an example, here's an A and here's a B. We can ask what's the angle between these two. We just use this. So we get the angle between these is pi over 3. So then we can say that A and B are perpendicular. What does that mean? That means that the angle between them is pi over 2, and that will be when A dot B equals 0. Because when they're perpendicular, the cosine of theta is 0, and that means that A dot B equals, well, actually from up here, if this is 0, that means that this is 0. And if this is 0, no. So anyway, when A dot B equals 0, we'll say that two vectors are perpendicular, but then you can ask, well, what about if A or B is 0? Then of course A dot B will be 0, but are they really perpendicular? Not really, but unless we just say that the 0 vector is perpendicular to every vector. So here's a quick example. If we take this vector and this vector, when we're thinking of this one, this looks like it's only in R2, but they're thinking of it as R3, so the z component is 0. So if you take the dot product, you get 0. So that means that these two vectors are perpendicular. Okay, so we have this notion of the angle between two vectors, like here's A and here's B. And something that's going to be useful for us is to ask, like if you shine a light down here, what is the shadow? How long is the shadow? And that clearly depends, among other things, on the angle between the two vectors. So if the angle is smaller, then it's going to be out here, and so on. If the angle is perpendicular, you can see that it's going to the length of the shadow is going to be 0. Now, it also obviously depends on the length of B. A, it doesn't depend on, actually, because we're thinking of A as just being the direction. And then A is forming the ground. So the ground basically extends everywhere. So it's not dependent on the length of A. It is certainly dependent on the angle between A and B. Here's another picture here. So here's the projection over here. This is called the projection, or we can just call it the shadow. One thing is the notation tends to confuse me. Like, does this mean the projection onto A of B, like the shadow shining down here, or does it mean like the shadow shining this way? So I don't know how to remember that, but anyway, this means the projection of B onto A. So I guess we can kind of call A the base. So we're projecting it onto the base. Okay, like when we talk about logs and we put this little number there, we call that the base of the log. So maybe I can remember it that way. So this probably comes from this situation or this situation where we have something sliding down an incline, and we ask what's the component of the force in this direction. Sorry, the force is in this direction, the gravity is in this direction, but we ask what's the component in this direction. So we actually want the projection of F into this direction. So this would be the A vector, and this would be the B vector. But anyway, we're not doing physics here, so we won't worry about that. But that's probably where it comes from initially, or one of the places. So we want to get a formula for the projection, and we're going to get it in two parts, because first of all, you should notice that the projection is going to not just be the length, but we're going to consider it to be a vector. So the length here, you can see the length is from here to here, but we're also going to say the projection is actually a vector, so it's the vector pointing in this direction that has this magnitude. So we're going to want two parts of this vector. We're going to want its length, which is the magnitude, and we also want the direction, which is actually just the direction of A. So what we're going to get is a formula for the magnitude. This is the magnitude. Here we have those two bars there. So this is that, and then we're going to multiply it times A, but we want to be careful. We don't want to actually multiply it. So we want to multiply it times A, because A is the direction. So this is the A vector, and we're just going to multiply it by A, but that's going to make it, if A is not the unit vector, then we want, we want to multiply it times a vector in the A direction, but just the unit vector, just the vector of length 1. So we have to modify A first. So we're going to do that, and we're going to end up with, so this is the modification of A. This is A, the vector A divided by its length. So that's going to change the magnitude of A. In fact, it's going to make the magnitude 1. But this is still a vector quantity, right? No, sorry, this is not, with the double bars around it's not a vector quantity, but this here is a vector quantity, right? Because this is A, and this is divided by a number, so a vector divided by a number is a vector. So this is the unit vector, and then we're going to, where did we have that? This was the projection. We're going to see that in a minute. We're going to take that projection, which is the magnitude. This is a magnitude times this vector. This is a vector, even though the top part is a vector. This is a number, so the whole thing is a vector. This is a number, so it's going to be a number times a vector. Okay? So that's going to give us the vector in this direction. Okay, let's, maybe that was too much. Let's see what we want. So I think from trigonometry, we know that this length divided by this length is the cosine of this angle, right? Cosine of this angle is defined to be this divided by that. So let's write that down. So the cosine of the angle is this divided by that. So this divided by that. And this is all in, we're not talking about vectors, we're just talking about lengths. These are the length of this divided by the length of this is the cosine of that. So that is what this says. Now, if theta is greater than 90 degrees, so if theta is greater than 90 degrees, the cosine is going to be negative, but this won't give you a negative. This will only give you, these are both positive numbers, so this is only going to give you a positive over a positive. So we have to put the absolute value signs around this in order to take care of that case. So then we can bring this b over to here, so we get this, and then we take that and divide and multiply and divide by the length of a, and this on the top. We go from before, we see that this is a dot b, absolute value. Let's make sure of that. So a dot b equals this, which is basically this. There's the absolute value sign there, but so we get a dot b over, this is called the norm of a, or the length of a, or the magnitude of a. So now we have the expression that we wanted, which is we have an expression for the projection of b onto a as this. This is our expression. Okay, so we just want to clarify one thing here. And they say, let k be any scalar and a any vector, then ka, the length of that can be written like this. And they say part 1 is left as an exercise. They say write out ka and write out that in terms of its components. Okay, so let's say that, anyway, it just basically means that if you want to take k outside of here, you can do it, but you just have to take the absolute value of k times this. Okay, so we'll accept that, or you can try to do what they said. Okay, the important thing is, what do we mean by a unit vector? In the direction of some vector, some non-zero vector, a. So the unit vector just means the same vector as a, but only has length of 1. So like in that picture, here's a, but this a we didn't say anything about the length of a, so this could be 10, this could be 100, this could be a third. But we want the same direction, but just vector of length 1. So this tells us how to get it. You just take the vector that the direction you want, and then divide by its magnitude. So they say to prove that, we want to show, this obviously is in the direction of a because it's just a times or divided by a number. So it's obviously in the right direction. So all we have to do is check to see that the magnitude is 1. So we want to look at the magnitude of this thing, which we just said from this property we can, well, no, sorry, right now we can just write it like that without any real, that's obvious. But now to take this outside, we can, as long as we take the, they didn't bother to put in absolute value sign, but it's basically already there anyway. So, so now you can see that you just get 1. So, so this over this does have length 1. It is obviously in the direction of a, because it's just a scalar multiple of a, or a scalar division of a. So, and we just showed that it has magnitude 1, so it is a unit vector in the direction of a. Now, we say, going back to here, we said the magnitude of the projection is given by this formula, so we just take this thing, which is the magnitude of what we want, and multiply it times the unit vector. So multiply it times this. This is what the unit vector is here. The unit vector, take that, and plus or minus, I guess we can go in either direction. So this is it, which now we can rewrite this like this. And what else can we do here? Well, yes we can. What else? What are they going to do here? They're going to put these two together, write this as the dot product. Yeah. So this is the dot product, which is here. These two together, here, those two, give us this, and then times this a. So all of this actually is a scalar, right? Because a dot b is a scalar. This is just the magnitude of something, so it's a scalar squared. So all of this is a scalar times a. And that is the projection of b onto a. So that's our formula that we need to somehow remember. I don't remember it, honestly, but let's see, is there any way to remember this? here's another form of it, because A dot A is equal to this thing squared. So I don't know how to remember this, but anyway, that's what we're supposed to remember. This is a formula for the projection of B onto A. And it's equal to A dot B over A dot A times A.